And we will speak about semi-definite programming hierarchy for geometric tracking problems.
Thank you, and thanks to the organizers for giving me the opportunity to speak here. So I want to talk about a hierarchy which can be used to upper bound the density of packing problems in discrete geometry. And this is based on the joint work with Frank Valentin. So I want to start by explaining what I mean by geometric packing problems and how these problems relate to maximum independent set problems in graphs. And then the main part of the talk will be about the definition of this hierarchy. And then at the end of the talk I want to briefly go into a few properties. In particular, the main result we have now that this hierarchy converges infinitely many steps to the optimal density. So here are a few examples of geometric packing problems. So the first is the spherical cap packing problem, or the spherical code problem, where you want to pack as many spherical caps of a certain size as possible on the unit sphere. The second problem is a circle packing problem in a bigger circle. And the third is a packing by cylindrical particles. So for all these problems, we can model them as maximum independent set problems in a graph on infinitely many vertices. So to see how this is done, we look at the first example, so the spherical cap packing problem. And here we want to know what is the maximum number of spherical caps of size t in the unit sphere, such that no two caps intersect in the interior. So they're allowed to intersect on the boundary, but not in the interior. And to model this, we use the graph G with vertex set the unit sphere, and 2 points x and y are adjacent if their inner product lies in the open interval T1. Now then the observation is that in this graph, the independent sets correspond to valid packing. So an independent set is a subset of the vertices which does not span an edge. So for each independent set there's corresponding packing and vice versa. And then we would like to know the independence number of graphs like these, because if we know the independence number, so that's the size of a maximum independent set, then we also know the optimal packing density. Well, and of course computing this independence number is a difficult problem. So even in finite graphs this is NP hard. So methods have been developed to get upper bounds. Of course constructions give lower bounds, but we also want to have systematic ways to find upper bounds. So I want to go over a few of those methods which are relevant to this talk. So I think the first systematic method was the Delft linear programming bound. This is for the specific problem of binary codes. So given a binary code problem with certain parameters, you can form a linear program, and then the optimal solution of this linear program gives an upper bound on the size of binary code. Now later a more general bound was given, the Low-Taylor number. This is a semi-definite programming bound, and can be used to upper bound the independence number of an arbitrary finite graph. Later this was a small modification was given, the theta prime number, and it was also recognized that if you apply this theta prime number to the binary code problem, so to the graph related assigned to this binary code problem, then it reduces to a linear programming bound, and you actually get the Delft linear programming bound. Now then a hierarchy was given of semi-definite programming bounds, which works for arbitrary binary polynomial optimization problems. This is the Laat hierarchy. We've heard about it before this week. And well, like what we saw yesterday, that the max cut problem can be written as a polynomial optimization problem, is a very similar way you can write the maximum independent set problem as such a polynomial optimization problem. So we can apply the Laat hierarchy to this specific problem. And this is what Laurent did. And here it was also shown that if you look at the first step in this hierarchy, so if you apply the Laat hierarchy to the independent set problem and you look at the first step, then you actually get the theta number. So you can view this specialization as a generalization of the theta number. And also in this paper in 2001, it was shown that this hierarchy converges infinitely many steps. But here for the specific problem, when you apply it to the independent set problem, Laurent gave a simpler proof. And what we want to do in this, talk, is generalize this Laat hierarchy to infinite graphs, apply it So the application of this Lassere hierarchy to the independent set problem, that I want to generalize to infinite graphs. And I also want to prove finite convergence. And for that we use some techniques used in the proof by Laat. Okay, so because I want to generalize the Lassere hierarchy, I want to first discuss it, how it works for finite graphs. So we have that the t step in the hierarchy, so last step t of g, is the optimal value of the following maximization problem. And the variables in this maximization problem are vectors y, indexed by the independent set up to cardinality 2t. And we had non-negativity constraints. So you wouldn't get these automatically if you apply the Lassere hierarchy to the independent set problem. But we just add them because, well, they're still upper bounds and it makes the analysis a bit easier. The objective function, there we sum over the entries of y corresponding to the vertices. And then we have constraints, so normalization constraint that the entry of y corresponding to the empty set is equal to 1. And from a vector y we construct a matrix MT of y, a moment matrix, and we require this matrix to be positive semidefinite. So here's the precise construction of the matrix. Its rows and columns are indexed by the independent set up to cardinality t. And the j, j prime entry is equal to the vector y at the union of j and j prime, given that this union is independent. Otherwise we set it to 0. Now then the result is that, well, the first step is equal to theta prime. So the prime because we added the non-negativity constraints. And then you get a hierarchy of bounds which get increasingly difficult to compute, but they also get better, and it's guaranteed that if you're at t is equal to the independence number alpha of g, it actually gives the independence number. So we want to generalize this to infinite graphs. So I want to first look at results where the Delsart bound and the theta number were generalized. So the Delsart bound was generalized for the spherical cap packing problem, the spherical code problem. And later also the theta number was generalized to infinite graphs. And it was again recognized that if you look at the theta prime number and you apply it to the graph corresponding to the spherical cap packing problem, you get the Delsart linear programming bound. So what we want to do now is generalize the Lassere hierarchy to infinite graphs, and I want to briefly discuss finite convergence. So we have to talk about to what infinite graphs we generalize. So the theta number here was generalized to distance graphs. I want to look at a slightly more general situation, but we cannot consider all graphs because, I mean, of course, the independence number of an arbitrary infinite graph isn't even finite, so it doesn't make sense to upper bound it. So the graphs I want to look at satisfy these two intuitive properties. So we want that vertices which are close, we want them to be adjacent. So if you think about the spherical cap packing problem, if you have two centers of caps which are really close, then definitely the corresponding caps intersect in their interiors. So there must be an edge. This is not a valid configuration in a packing problem. And also, the second condition, we want adjacent vertices to stay adjacent if you perturb the vertex a little bit. So again, if you think about spherical caps, if you have two caps which intersect in their interiors, if you perturb them a little bit, they will still intersect in each other's interiors. So we want to formalize these intuitive conditions in a definition, and for defining what it means to be close, we use topology. So we say that a topological packing graph is a graph where the vertex set is a Hausdorff topological space, and each finite clique is contained in an open clique. And of course, you only have to check this definition if you want to check that a certain graph is a topological packing graph for cliques of size 1 and 2. The rest will follow automatically. Now, if you look at this definition, then actually you can see that any graph is a topological packing graph by just assigning the discrete topology to the vertex set. But the idea is, if you take a weaker topology, then you actually put constraints on the edge set. And what we will do is we will consider compact topological packing graphs. And then also the independence number is finite. So this is easy to see. Each vertex is a clique. So each vertex is contained in an open clique. So you get a cover of your vertex set by open cliques. By compactness you get a finite subcover. So your vertex set is covered by finitely many cliques. And of course an independent set can have at most one vertex in each clique, so the independence number is finite. So here's the generalization. The teeth step of the Lasserre hierarchy is equal to the optimal value of this maximization problem. And now as variables, we take radon measures, non-negative radon measures on the set of independent sets up to cardinality 2t. And of course for this definition to make sense, we also need to talk about the topology on the set of independent sets, so that will come later. For the objective function, we evaluate the measure at the set of independent sets of cardinality 1. So in the hierarchy for finite graphs we would sum over all vertices of the graph. That's what we do here, but we have to put the vertices in singleton sets for this to make sense. So that's why we use the notation the set of independent sets of cardinality 1. And then we have the normalization constraint. So if we evaluate this measure at the set containing the empty set, it must be equal to 1. And for the positive definite constraints, we use this. So we have some operator, AT star. We apply it to lambda, and then this has to be in a certain cone. So I'll also talk about the exact definitions of this operator and this cone. So first for the topology on I2T. Well, we need a bit of extra notation. So let sub TV be the set of non-empty subsets of cardinality at most t. So this also includes the non-independent sets, but it does not include the empty set. And then we have a quotient map, a surjective map, going from the t-th power of v to sub tv, and it maps a t-tuple to a set. And of course in this tuple you can have repeated entries, so you actually get, so this map is actually surjective. And then, since we consider compact topological packing graphs, we have a topology on the set V, and this gives a topology on the t-th power. So we can use the quotient topology on sub TV. And now our set of independent sets is a subset of sub TV if we add the empty set. So by using here the disjoint union topology and then the subset topology, we have a topology on the set of independent sets. So the next thing we need to look at is this cone, how it's defined. And we define it by using a dual approach. So we first go to the cone of positive kernels. So we say that a function, a continuous function on the product, which is symmetric, we say that this is a positive kernel if the following equation is satisfied. Well, you can view a positive kernel as an infinite matrix where the rows and the columns are indexed by the independent sets up to cardinality t. And then this condition says that all finite principal submatrices must be positive semidefinite. Now these positive kernels form a cone for which we use this notation. And then by the Ries representation theorem, the dual of the space of continuous functions is the space of radon measures. So we use duality to define the cone of positive definite measures. So we say the cone of positive definite measures is the set of all radon measures, symmetric radon measures on the product, such that if you integrate it against a positive kernel, you get a non-negative value. Okay, so now for the definition of the operator. We again use duality, so we first go back to the finite case. And there we observe that going from this vector y to this moment matrix, that's a linear map. So here in this identity, on the left we have a trace inner product of matrices. On the right we have a regular inner product of vectors. So there is some operator AT, they're joined, such that this identity is satisfied. And now what we do, we don't generalize MT to the infinite setting, but we generalize this map AT to the infinite setting because that's easier to do. So if you do that, we get the following definition. So we say that AT is the operator going from the symmetric continuous functions on the product to the continuous functions on I2T. And we define it as follows. So if we evaluate the function ATF at the set S, then we sum the function f over all j and j prime in IT whose union is S. Now then, we use duality, the joint operator, to define AT star. And this is an operator going from the radon measures on I2T to the symmetric radon measures on the product of IT with itself. Yeah, here it's not needed, I think, but later we will use it. So we endow the space of continuous functions with the weak topology, the space of radon measures with the weak star topology, and there you're in a symmetric situation. Yeah. Okay, so now we finished the definition of the hierarchy, so we can look at a few properties. The first property is a duality theory. So this is important if you want to do concrete computations. Because in the maximization problems, we need optimal solutions to be sure that we actually have an upper bound. But in the dual minimization problems, we only need a feasible solution to ensure that we have an upper bound. And of course, in finite semidefinite programs, this doesn't really matter. I mean, the solvers are primal dual solvers anyway, but in these infinite programs, if you do computations, you want to do some reduction first. And that usually means that you only can prove that you have a feasible solution. You cannot usually prove that you have an optimal solution. Well, if you do that here, we view our optimization problems as conic programs. So then we get the dual by conic duality. We use the notation last sub t of G star. And the important thing here is that we optimize over positive kernels. Okay, so in concrete computations we want to use these minimization problems, but what I will show in a moment is that we have finite convergence for the maximization problems. But we would like to know that then this also holds for these problems, and for this we need strong duality. So we have the result that strong duality holds, so for each t, the primal and the dual attain the same value. And also, given that the maximization problem is bounded, the optimum is attained. So I want to go over the idea of the proof here, also because I think it might have a broader it can be applied in a broader setting, I think. So I think it's interesting to look at it. So for proving strong duality, we'll use a closed cone condition, because I mean interior point conditions don't usually work in this infinite dimensional setting. And for instance, this condition, you can find it in the book by Barvinok. And well, if you apply it here, we need to show that this cone is closed in the space below, where we have the weak star topology on the space of radon measures. Yeah, we use a xi now instead of a lambda because it's now normalized at 0 instead of 1. Now the trick we have to show that this is closed is that we decompose it. So we write it as the Minkowski difference of two cones, K1 and K2, where K1 only involves the measure xi, and K2 only involves the measure mu. And then we use a theorem by Klee and Dieudonné that a Minkowski difference of cones in a locally convex topological space is closed when the intersection is trivial. Both cones are closed, and one of the two cones is locally compact. So here we show that the K1 is locally compact. And actually it's good that we don't require both cones to be locally compact, because we also showed that if the graph is infinite, then actually K2 is not locally compact. Okay, so now we can go to the main result we have for the hierarchy. And that is that if K is a compact topological packing graph, then also in the finite step, the independence number is attained, so the optimal density is attained. So I want to briefly sketch the proof. Well, the first observation here is that if you have an independent set, then you can form a feasible solution as follows. So we define a measure chi as by taking the sum over Dirac delta measures delta r for all, where we sum over all subsets R of S. And this is a feasible solution for the optimization problem. And now we like to go in the other direction. So we take a feasible solution and we want to write it in terms of these feasible solutions. So if you have a feasible solution lambda, then we can write it as this vector-valued integral. So we integrate the measures chi s against some signed Radon measure sigma on the independent sets. So this resembles a linear combination. And then the main part of the proof consists in showing that this measure sigma is a probability measure. So that this integral here resembles a convex combination, and the chi s are the extreme points of the feasible region. Non-negativity.
Sigma.
Yeah, actually, yeah. If you prove non-negativity, it's almost immediate that it's a probability measure. Yeah. So that's actually the main part of the proof. So and if we know this, we can substitute this formula integral for lambda in the maximization problem, and then we get this maximization problem. So we maximize the integral over the cardinality of S against this measure sigma, where sigma is a probability measure on the independent sets. Well, then of course the cardinality of S is at most the independence number, so the maximum is at most the independence number. Oh, it's also attained, so we have equality, that the Lasserre hierarchy in the finite step attains the independence number, even if the graph has infinitely many vertices. So if we go back to the geometric packing problems we saw on the first slide, these can be modeled using a compact topological packing graph. So the hierarchy applies in that setting, and now we have the result that infinitely many steps this hierarchy actually attains the optimal density. Well, and of course computing these values is very difficult. I mean, yeah, so the theta number has been computed for certain infinite graphs. For instance, for the circle code problem, the circle cap packing problem, the theta number has been calculated. And also improved bounds have been calculated, like 3-point bounds. And the techniques used here are harmonic analysis to do the symmetry reduction, and then semidefinite programming. Well, we believe that these techniques can also be used to solve these problems, find good feasible solutions to the minimization problems. So what this shows is that this method of using harmonic analysis and semidefinite programming to find upper bounds on the density of packing problems can, in fact, in theory at least, can in fact solve these problems.
Sorry, so it doesn't tell you anything about the functional form of the dual solution.
Sorry?
So this doesn't tell you anything about the functional form of the dual solution. The eigenvalues of the
No, so
of this would be arbitrarily complicated.
yeah, definitely. So the idea is that you have a good candidate for an optimal solution, optimal packing.
But you could not even approximate them with any kind of nice functional form.
So what do you mean in the maximization problem or the minimization?
I mean, somehow the eigenvectors of that term,
Yeah.
right, then you could be arbitrarily complicated.
Yeah, definitely.
So I mean, somehow, what does this finite termination condition actually tell you?
Well,
Completability.
yeah, so it tells us that if you are in the final step, the optimal value is the independence number.
But you cannot represent those.
No, in concrete computations, of course, you use a Fourier transform of this kernel and you truncate it at some point. So you get a feasible solution. You don't get the optimal solution. So, yeah, so of course, for certain problems, this will be a very good solution and you can get very close. But you're right, you cannot, even in the minimization problems, the infimum might not even be attained. We only prove this for the maximization problems. So you're right, if you do concrete computations, you need to truncate this Fourier transform, so you get hopefully good feasible solutions, but you don't get optimal solutions. Yeah. Yeah, so this is actually what I wanted to tell, so thank you.
May I ask a question related to the last slide?
Yeah.
So, are you actually using basically you need to prove that sigma is a probability measure because you need to include the Dirac measure on the optimal on the maximum stable set, right? To show that it's feasible for this program. But in fact, you only need that the total variation is equal to 1. You can even deal with signed measures, right? You need this inequality that this integral is less or equal than
Yes, yes.
no. That
So
well, why do you need that sigma is a probability measure here?
well, if it's a signed measure, then
With total variation 1.
yeah,
Then
then
it includes all probability measures, and it also includes the Dirac measure concentrated on the maximum.
no, I mean, if you want to show that any feasible solution lambda can be written as this integral where sigma is a probability measure. That's the idea.
Yeah, but do you really need this? This is my question.
Yeah, I think so. So let me think.
Because the Dirac measure concentrate supported at the maximum stable set is of course a signed measure with total variation 1.
No, I don't think so. Let me think.
It's a probability measure, but and therefore the total variation is the total mass, which is 1. But probably this is too special to be discussed.
Yeah. Let me think about it. I'm pretty sure we need it to be a probability measure, but
But a general question then, you spoke about the quotient topology and then adding the singleton of the empty set.
yeah,
Is this then an isolated point for the
exactly. Yeah.
How can this be applied to something like the cylinder packing problem? Because there, the orientation of the cylinders.
Yeah. So your vertex set then is not only the location of the cylinder, but also its orientation. So you get a very complicated vertex set. In fact, even for that problem, the theta number is already very difficult to compute.
John?
When you converge at the alpha g step, is it equivalent, this condition of saying that the moment matrix has a finite rank? I mean, if you go one step further, the rank stabilizes?
I don't know. We didn't think about that.
So for those classical Hamming code problems, when you exploit the symmetry, the SDP actually reduces to an LP, right?
Yes.
Does the same happen for some of your problems?
No, I don't think so. So, I mean, we didn't do computations yet for the second step. So, but no, this will not reduce to a linear program. This will be a semi-definite program.
Thank you.